right, so we're picking up where we left off on the lecture about matter. And we were about to talk about different states of matter, which remember is a physical property, meaning when matter changes from like solid to liquid or liquid to gas, that would actually be a physical change. It doesn't turn a substance into a new substance. So solids, liquids, and gases, these are the three main states of matter. There's a fourth one that I'll mention, but you won't really focus on that in here because you wouldn't encounter that one in your classroom. So just taking a look again, if we think about water, H2O, solid water or ice is H2O molecules of water, but they're really tightly packed together and they're locked in place. When we melt that to liquid water, now the molecules can slide past each other. And finally, in a gas, when we boil away water into steam, the molecules are getting even further apart. They actually have a lot more energy and they're bouncing around. They've lost their attractions to one another. So we haven't turned water, H2O, into anything else. When you boil water, it doesn't break into hydrogen and oxygen. When you melt ice, it doesn't change the chemical formula. So first, let's talk about solids. So in solids, they have what's called a definite shape and a definite volume. That means a solid, if I put an ice cube on the table, assuming it's not melting, it's going to hold its shape. That's a definite shape. And it takes up a specific volume of space. In a solid, not only are the particles tightly packed together, but they are in fixed positions. The attractions between them are extremely strong so that this molecule, or this atom, can't slide past these. It can only sort of vibrate in place. Interestingly, when you heat a solid, these vibrate faster and faster and faster until they have enough energy from heating them that they can actually move. And once that happens, now you have a liquid. So in a liquid, now the particles are still attracted to each other, but they have the ability to move around and slide. We say they flow past each other. But there are still attractions. This one couldn't just break away and float into the air. It's kind of stuck with the other liquid particles. Now, they have a definite volume. For example, I can measure out 100 milliliters of water, and that amount would be a definite volume. But they don't have a definite shape. If I pour it into a beaker, and then I pour it into a test tube, and then I pour it onto the floor, it's going to sort of spread out and take the shape of that container. Again, the atoms are close together. For the most part, in a liquid, they're further apart than they are in a solid. But the most important thing is that they're not stuck in place vibrating. They now actually have the ability to flow. Now, if I boil this away and turn it into a gas, interestingly, these now are getting more and more energy and they're flowing past each other faster. And eventually, they can get enough energy where they escape the surface. And that is now going to become a gas. So gases have an indefinite volume, meaning if I don't close it up in a container, it'll just spread out. The molecules will just get further and further apart. And of course, they have an indefinite shape. So if I had a vial and it had the smoke from a stink bomb, and I unscrew that, the smoke would sort of just spread out and the molecules and atoms would randomly bounce around the room and they just keep spreading out forever. The molecules or atoms would be very far apart and there'd be no attraction. It's not like when this one hits this one, they stick. In a gas, they have enough energy that they just would bounce off each other and keep going. Now that fourth state I mentioned is plasma. And we're not going to talk about that much in this class, but they have an indefinite shape and an indefinite volume. And the particles have so much energy that they ionize. They actually, ionize means they lose some of their electrons. So if you look at the picture, you see how there's positive and negative charges here. They're very spread apart as well, like a gas. An example of plasma is lightning. It's not something you can, look at, like I said, per se in a classroom on a normal basis. So solid, liquid, and gas, since we're studying chemistry, we'll be really studying these three phases of matter. All right, water is actually a little strange. If you've ever put a water bottle in the freezer, or you've ever put a can of Coke in the freezer and you forget about it, you'll notice that the water bottles swell up and the can actually explodes. And that's because water has some very unique properties. And we're going to talk about that a little more in another chapter, but I wanted to point it out because it sort of breaks one of the rules that I just told you. Normally, solids are more dense, they're more tightly packed than liquids. Water does something weird. When it freezes, the molecules actually push further apart. It takes up more space as a solid than it does as a liquid, and that's actually why ice floats and why soda cans explode in the freezer and your water bottle may get all bloated in the freezer, is because although the water molecules do get trapped and locked in place in a solid, they're actually forced further apart in the solid than they are in the liquid. Now, vapor. When you hear the term vapor, it's not exactly the same as a gas. Vapor is where you have a substance that's normally a liquid or a solid. So think about water. Water is normally a liquid, but you know how it is when it's humid outside, right? Humidity is really water vapor, little particles of water that have evaporated, and so they are in a gaseous state, but that's not the normal state that they should be in at this particular temperature. So a gas is something that is normally in that state at room temperature. So for example, oxygen gas. At room temperature, oxygen is a gas. Water is a liquid. So any water particles that are in the air as humidity, that would be called a vapor, not a gas. It's just a little nuance there. All right, so physical changes versus chemical changes. A physical change is anything you do to a substance that doesn't actually turn it into a new substance. So if I grind up rock salt into powder, if I cut a piece of paper, if I melt an ice cube or boil water, none of those actually change the substance into something new. So this includes changes of state, solid, liquid, gas, and then it also includes simple things, like I said, like cutting, grinding something up, ripping a piece of paper in half. These would all be physical changes. I haven't turned the atoms or molecules, I haven't changed their arrangement into a brand new substance. Chemical properties, on the other hand, can only be observed. They have to do with how something reacts. You observe a chemical property by a chemical change, if that makes sense. So it's how a substance reacts. You would always have reactants on the left when you see a chemical reaction, and products are on the right. A chemical reaction would tell you some of the chemical properties of something. For example, if I put magnesium into hydrochloric acid, I get hydrogen gas bubbling. In fact, you saw some chemical changes when you did the Baggy lab, and you saw bubbles and the color changed and all that. You turned the baking soda and the calcium chloride, they reacted with one another. They made carbon dioxide gas, so they made something new. The atoms got rearranged into different molecules. So if something burns, you burn wood, you've turned it into ash and carbon dioxide and water vapors and things like that. You don't have wood anymore. But if you just chop a log in half, you still have just 2 pieces of wood. Does it react with other substances? Things like that. So physical versus chemical, iron and sulfur. If I mix them together, I would have a mixture of just iron and sulfur. That would be physical. I could use a magnet to pull the iron out. So I wouldn't have to do something chemically to separate them. But if I was to heat them and put them through a chemical reaction, I would get a brand new compound, iron sulfide. And that compound would have completely different properties. It would no longer be magnetic. Sulfur is actually yellow. This would no longer be yellow, the sulfur. The iron would no longer be a shiny metal. So the properties would completely change. So that would be chemical. So if I burn gasoline, this is chemical. I literally am putting it through a chemical reaction where that gasoline breaks down into carbon dioxide and water. I've rearranged the atoms of gasoline and the gasoline is gone. The atoms are still there, just to clarify. Octane, I think it's C8H18, and when you burn it, you're using oxygen. So the oxygen still ends up on the other side, but now it's been rearranged into the carbon dioxide in the water. And the carbon is here, and the hydrogen ends up over here. So the different elements get rearranged in a chemical reaction. If I evaporate the gasoline, if you just let gasoline sit outside, it'll evaporate into a vapor, but it's still gasoline. You would still have the same chemical formula just floating around. There is a law called the law of conservation of mass, and there's actually a similar thing, law of conservation of matter. Basically says matter isn't created or destroyed, mass also isn't created or destroyed. The mass of the products that you make should weigh the same as the original reactants you started with. And that can be tricky because, for example, if you burn wood, you might say, but the ashes weigh way less, right, than the wood did. But don't forget that when you burn it, you'll see smoke coming up. Some of that stuff's floating away. Some of it is carbon dioxide. Some of it is water vapors that were trapped in the wood. So you have all sorts of other things that float away. And so, yes, the ash weighs less, but if you were to capture the smoke and everything else that came from burning it, it should weigh exactly the same. All right, mixtures. Unlike substances, mixtures are a physical blend of two or more substances. Most matter is actually found as mixtures. Air is a mixture of gases, for example. Chicken noodle soup is a mixture. The chicken keeps its properties. The noodles have different properties. In air, you have oxygen, which has the properties of oxygen. You have nitrogen. You have carbon dioxide. And each of those are floating around, but they keep their individual properties. Remember how that's different from, say, chemically combining sodium and chlorine. Sodium was a metal. Chlorine, green gas. Combine them, table salt. They lose their original properties. Oxygen in the air is still oxygen. Chicken noodle soup, the noodles are still separate from the chicken. Gasoline is actually a mixture. Octane is the important substance, but it's also got ethanol and some other things in it. So gasoline's not really pure octane. In fact, that's why if you've ever been to the gas pump, you'll see like 89, 92, like the different grades of gasoline. It's the percentage of octane in the gasoline mixture. So just to show you, a mixture of elements. Remember, oxygen, even though this is a molecule, it's still a single element. So this would be a mixture of two elements, neon and oxygen. This would be a mixture of compounds. Carbon dioxide is one compound, and water is another. So this is a mixture. And this is a mixture of elements and compounds. So you have oxygen, which is an element, carbon dioxide, which is a compound, and water, which is a compound. So those would all be examples of mixtures. And each individual part there would keep their own properties. You haven't created anything new. Homogeneous and heterogeneous mixtures, very quickly. Homo means the same, hetero means different. So a homogeneous mixture is one that sort of appears the same throughout. Whereas a heterogeneous mixture, you can see the separate parts. Chicken noodle soup is a very obvious heterogeneous mixture. You can physically see the parts in it. All right, so a little more detail about homogeneous mixtures. The composition is uniform throughout, meaning it's going to look the same the entire way through. Copper chloride solution is a solution that's a homogeneous mixture. The word solution, this is actually a word for a homogeneous mixture, although usually when you think of like peroxide solution or 70% isopropyl alcohol solution, you usually think of liquids, but you can actually have a solution of gases or a solution of solids. We just usually use the word when we're talking about liquids. So normally, if you can't see separate parts, you usually can think of it as a homogeneous mixture. Think about steel. Steel is a mixture of metals. 14 karat gold is a homogeneous mixture. It's actually several metals combined to make it durable, but it looks the same throughout. Vinegar is another one. It is a homogeneous mixture. Can be tricky. Blood, for example, and milk are heterogeneous mixtures. Even though looking at it, they look the same throughout. We'll talk more about that later. We're not going to try to trick you on a test. These, it's because of the particles, the size of the particles in it, that they're not actually considered homogeneous, but don't worry, you won't be asked one like that. Phases are the parts of a sample. A homogeneous mixture only has one phase, whereas a heterogeneous has two or more.